Let's continue talking about thermodynamics in kinetics of reactions. And we were saying that about this reaction, say for example, A plus B to give C and D, and we drew a profile for that. And again, if we have this, the process is exergonic. If this is A plus B, and this is CD, this is reaction coordinate, so this is G. We can say that the change, what it matters to us in thermodynamics, what indicates the position of the equilibrium is the difference between reactants and products. And then we're going to write that the change in free energy for the reaction, say products minus reactant, is related to RT, and this is your the logarithm of the K of equilibrium. And we have defined the K of equilibrium. Taking anti-log here, you can calculate the K of equilibrium as A to the negative delta G over RT. So we can do that. We talk about that is thermodynamics depends is on the difference in energy this between products and reactants. Now when we're talking kinetics, and we said it in a previous video, we are talking about this changing energy. And that's the barrier to go to products. That's your transition state, so that will be the difference between energy of transition state in the rate determining step when there's more than one. Here we only have one step, but now we can relate that change to the rate, and we can say that this relates to the change in energy of activation to that barrier. So that's kinetics. That is what you will see, that rate, and that change in delta G is where you see the, in the case, say, the position of the equilibrium. So if the process is reactant favor or product favor. Now, let's do something else here, another profile. Let's say that I have a profile just now like this one. That's a different reaction. Here I have again G, reaction coordinate. If this is reactants and this is products, again I see that reactants are below here, so less the difference here in, let's do a dotted line between reactants and products is this amount. So delta G is negative. So this reaction is exergonic. And that means product favor. Also, I see that this reaction is happening in two steps. Here we have step one is from this point, reactants, to this local minimum here. That's called an intermediate. And then we have a second step from the intermediate to products. We also see here that we need to cross a barrier. That's one transition state. And then from the intermediate to products, I have another transition state. Also, we see that is the energy of activation. So now, what I want to do is, let's draw a profile more complex and see if we identify how many steps we have, how many, if we have intermediates or no. So let's draw, I'm going to erase that to give you a profile that's more complex. And see that. Is kind of erase quick, right? Don't waste too much time. Okay, let's do this now. Let's draw a profile. Show little dots there. Okay. Let's say that I have a question on a test, ask me several things. And I'm going to draw first, and then we're going to say put different questions. Reaction coordinate. free energy, right? And I'm going to say identify things that are in the in this diagram, in this reaction profile. First, let's say if I have a question saying, is the reaction exergonic or endergonic? So, and here, how do you answer that? You will look at the difference in give free energy between reactants and products. And now it is this. Delta G here is positive. So you answer to the question is this process is endergonic. And also that says it is endergonic, and that means it's reactant favored. Okay. Now say that you have another question on this profile. And the question says, how many steps do you have? How many steps? So here we're going to identify the steps then. Here I have one. I'm going to draw a line. Step 1. Then step 2. Step 3. And you can also have saying identify what are if we have intermediates and how many intermediates. So identify intermediates and how many. Okay, so remember intermediates are local minimum in this curve. So this is a minimum, this is a minimum. So this reaction profile has 2 intermediates. I'm going to name it intermediate 1, intermediate 2. So my answer here, I have 2 intermediates. Reaction is 3 steps, 2 intermediate. The reaction is endergonic. Reactants, products, we say that. Another question here. How many transition states? How many transition states do we see here? Now, the transition states are max in the curve here. So here I have 1 transition state. This transition state is leading to the formation of the first intermediate. Then I have another transition state when you go from intermediate 1 to 2, and then you have a third transition state. So a reaction in 3 steps will have 3 transition states, 2 intermediates. And now, if you're being asked about what is the energy of activation, say that you had numbers here, 1, 2, 3, I'm going to make a scale saying kilojoules per mole, arbitrary. And say that the question say, calculate the energy or estimate it by doing the graph. And this was kJ per mole. For example, what you will do in this case is find out what is the difference. Here is your rate determining step, the slowest, and you will find the difference in energy between the transition state of that step, the slowest, and the reactance. So it is this much, and we're going to subtract. This is approx 7 minus 3 that you will see here. So this much is apparently, it is 4, right? 7 minus 3, so it's 4 kJ per mole. So if you had a diagram like that, if you're being asked what is the difference in energy, say here, the change in free energy, let's say that I'll do that. Well, apparently it was, that difference is 1 kJ, so very small. I just made an arbitrary scale so you have an idea. But if you had these numbers, then you would be able to calculate, say, this by the rate constant. And you will also be able to calculate from this difference the equilibrium constant, which is E, that's not. And also notice that when we have said that in a previous video analysis, when we did the analysis of thermodynamics, if this number is a positive number, all of that is negative, the equilibrium constant is small, it's smaller than 1. So that also says the reaction is reactant favor.